So exercise 5, let's do it. First question. Find the moment of inertia of a half disk about an axis perpendicular to the plane and passing through its center of mass. Come on, what kind of thing is mass is m, radius is r, whatever. So I mean it's pretty much same thing as a full disk, because I mean the distribution is very much similar. It's going to be mr squared upon 2, but still let's just do it. So it's going to be half of so if it was a full disk, it would be 2m times r squared and that thing upon 2, right? But now since it's just a half disk, and yeah, like it's just half of the inertia, because yeah, like the summation of mi r squared, that's going to be cut in half, and yeah, it works out. You can see that it's just going to be mr squared upon 2. So first one, really, what was this? Yeah, okay, second. Uniform rod EB of mass M is released from rest when beta is equal to 60 degrees. Assuming that the friction force between A and the surface is large enough to prevent sliding. Okay. Determine for time just after release. Okay, the angular acceleration of the rod. Okay. Normal reaction and friction force at A. Okay. Minimum value of mu but compatible with the describable motion. Fine, fine, fine. Let's do it. So first of all, what is the angular acceleration? Is just going to be angular acceleration is just mg times L upon 2, and yeah, mg L upon, but wait a second, actually it should be mg cosine beta L upon 2, right? That's the torque upon the inertia, which is ml squared upon 3. There we go. That's our angular acceleration. This cancels. It is going to be 3 upon 2g cosine beta upon L, whatever. So once you know this angular acceleration, I mean, okay, that's just so first we got it. A, that is just going to be 3 upon 2g cosine beta upon L. This is okay. What about B? Normal reaction and the friction force at A, fine. So this torque is also just going to be equal to right. So the gravity acting on the center of mass doesn't actually produce any angular acceleration about the center of mass. Only the other thing will produce. So what is the other thing really? You got friction force in this direction, maybe. I'm assuming it's in that direction. I don't know. Maybe it's going to be. Yeah, I mean, yeah. The center of mass is moving towards right? So the friction should be in this direction. So you got F over here. You got normal force like that. That's what this rod is like. Okay, and the torque because of these things. So this is beta over here. That's going to be 90 minus beta. So it's just going to be F cosine. Sorry, torque, right? Sorry. And we want it to go anti-clockwise. So friction is opposing that motion. So it's going to be N times this angle is going to be beta. And it's going to be 90 minus beta. So N cosine beta minus that times L upon 2 minus so you got F over here and cosine of this sine beta. So F sine beta L upon 2. That's the torque upon the inertia. Upon the inertia as seen by the center of mass. I mean, yeah, like you get the idea. So that's going to be ml squared upon what was I doing once again? Yeah, ml squared upon 12. Right, which is also equal to the angular acceleration. So from here you can write one equation. You will also need another equation. First of all, let's simplify this thing. N cosine beta minus F sine beta. So you got L upon 12 upon 2. You got L squared upon and L and then 6. That's equal to this thing. So 3 upon 2g cosine beta upon L cancels. Yeah, you got okay. This cancels. It's gonna be 4 over here or whatever. I mean, okay, just put 4 over here. So this is just n cosine beta minus f sine beta is equal to, well, let's see. You got this g over here and oof, what was I doing? Sorry. Oh yeah, what was I doing? So mg upon 4. Yeah, right. And yeah, we don't like that. It would be better if I could change this a bit. Whatever. The other equation was, where to go? Right. The equations of motion, I mean the translational equation. So this guy's acceleration, I mean this guy's acceleration is a in this direction, so a in this direction, and that's why you just want in that direction completely. Yes. It's also got centripetal acceleration in this direction, right? And of course there's gravity and everything which is doing it. Ooh, it's going to be hard to write all of that down. Okay. uh yeah, right, I think the this might not work, you know. So this equation that it's going with with alpha r in this direction, is this even, well, I think it's already I mean that can be derived from these two equations. I guess so. All we need is just another equation, one more equation. That's it, right? So, oh yeah, and its velocity is zero. So like this component is going to be zero. Oh, perfect, right? Yeah, I mean this component has to be zero. So you got gravity in this direction, and then because this component has to be zero, you can just take the components, and that will work out. It's got to have cosine beta right there. So this is still there, right? Oof. So this will be, okay. This angle is going to be 90 minus beta. So cosine of that thing is going to be mg sine beta is equal to, let's see, n cosine of whatever this is, n sine beta minus f, sorry, yeah, plus f cosine beta is equal to this thing. Now I know. What I think is that this looks something like a rotation matrix. Okay, so this looks like this vector n times f, and then all, yeah, I mean you get the idea. You could always solve this using the normal stuff, but then I could always write it as a rotation matrix, or maybe like complex numbers or something. What I'm thinking of is just multiply each of these by iota, and then add these two equations, and then together these would basically represent n times e power I beta, and then you got plus f times so fi e power I beta is equal to, well, you got mg, oof, well, that's upon 4 over here, which is that's not exactly what we want. Oh yeah, so you got 6 right there, and it's supposed to be 3 upon 4. Huh, something didn't work out the way I wanted it to. So let's go upon 3 right there, and that's L upon 2 granted. Right, everything seems to be working fine, but then for some reason you got this and not. Okay, it's not like that anymore. You got this 4 stuff over here, and yeah, yeah, we cannot do it right away. I mean, it would be nice if we could just rotate and get the thing done, but okay, that's not correct. Fine. So we'll have to deal with it. Like, yeah. What do we do? I guess just multiply this thing by cosine beta, this thing by sine beta, and then add these up. Right, add these up. So this is going to be normal is equal to mg, and then you got cosine square beta upon 4 plus sine square beta. So from here you can figure out the normal force. I guess it's correct. Did I make some kind of mistake? You got the angular acceleration as 3 by 2 g cosine beta upon n, and then you also got it like this because, yeah, because of this, right? It's ml squared upon 12, right? Yeah, I mean ml squared upon 3, but then the L value is now L upon 2, and the mass is still the same, in fact. So yes, it should be ml squared upon 2, and it works out, I guess. You got 6 over here, and then you got, yeah, it's all correct. What could possibly go wrong? I think it's correct. Okay, so you got normal force. So B, you want the normal reaction and the friction force at A. So just write down the normal force. It's going to be this guy, mg upon 4, and then you got cosine squared beta upon 4 plus sine squared beta, and then the friction force is just, yeah, I mean, right, we're gonna do that thing. So we'll multiply this equation by cosine beta and this equation by sine beta, and then we'll subtract, so we'll get the friction force in that way. So this will be sine beta cosine beta, and then you got mg minus mg upon 4, so 3/4 of mg. That should do it. So it's going to be 3/4 mg sine beta cosine beta, right? Okay, cool. Next. Third. Third is, we just also have to do C, sorry. The minimum value of mu compatible with the described motion. I mean, okay, wait, did I miss something? Oh yeah, there's also the centrifugal acceleration. But okay, that's zero, right? Ah, that's how we got this thing. That was one equation, right? And then you also have the tangential acceleration, but then I think that would be redundant to write because alpha and all this. Why, right? Okay, so let's go to now C, minimum value of mu compatible with the described motion. Um, oh yeah, so you got friction force, you also got normal force. What should happen is that friction should be less than or equal to mu times normal. So really 3/4 of sine beta cosine beta should be less than or equal to mu times, so mu upon 4 I should say, of cosine squared upon 4 plus sine squared. 4 cancels. Yes, this is what we're looking for, I guess. Okay, and now what do we do? This is some weird thing. 12 sine beta cosine beta is less than or equal to cosine squared plus 4 sine squared, or cosine squared minus 12 sine beta cosine beta. Did I mess up somewhere? Uh, Wait, how did I get this mg upon 4 though? Oh no, this has to be mg, not mg. Oh yeah. Yeah, that's not supposed to be mg upon 4 because we didn't get that. We didn't get mg upon 4. No, it was just mg cosine beta upon 4 and mg sine beta, just like that. And we did the whole thing and we got this value, not mg upon 4 times all that stuff. Okay, that's not what we were doing. So it's just not there. So then this is just 3 sine beta cosine beta. I got 4 over there. I'm gonna send it over here. So it's gonna be less than or equal to cosine squared plus 4 sine squared. Does that make sense? So cosine squared minus 3 sine cosine plus 4 sine squared is less than or equal to 0. But 4, 2 into, no, it doesn't work. What's the discriminant of this guy? Well, 9 minus 4. Oh no. Oh no. There's no such value compatible. Okay, this is, oh, mu times, sorry, mu times all of this. How could I forget that? So mu should be bigger than or equal to 3 sine beta cosine beta upon cosine squared beta plus sine squared. I'm gonna leave it like that because, yeah, they gave beta as one of the known quantities. So we'll leave it like that. Did they say it doesn't slip throughout? No. Okay, it just says right away it doesn't slip. So there we go. That's our value. So that's the minimum value, 3 sine beta cosine beta upon cosine squared beta plus 4 sine squared beta, I guess. Okay, let's go to third. By pulling on the cord of a yo-yo just fast enough, a person manages to make the yo-yo spin counterclockwise while remaining at a constant height above the floor. Wait, what? Constant height above the... So its y coordinate is not changing. Denote t. So yeah, I mean, in that case, the force on this guy should be equal to mg, right? So t is equal to mg. Got that? Denote the weight of the yo-yo by w, the radius of the inner drum on which the cord is bound by r, and the radius of the gyration of yo-yo by k. So radius of gyration is like, okay, that's just saying the inertia is m times k squared, right? That's all it's saying. Determine tension in the rod. The tension in the rod is like piece of cake because if its y coordinate is not changing, the tension must be equal to mg. The weight is what? I mean the mass. It did not give us. Oh, okay. So weight is w, and that's why this shows be w. Okay, cool. T. The angular acceleration of the yo-yo. Okay, so you got this force w in this direction, and then w times r upon the inertia, which is just basically mk squared. But w is basically like mg. It's just going to be g times r upon k squared. That will be your angular acceleration. So yeah, this wasn't so bad. Okay, next question. Fourth. A rigid body is made of three identical thin rods, each of length L, fastened together in the form of a letter H. The body is built to rotate about the horizontal axis that passes through one of the legs of the edge. Okay, what? Horizontal axis. Oh, okay. So it passes through this thing. Uh-huh. The body is allowed to fall from rest. What? Body is allowed to fall from rest from a position in which the plane of H is horizontal. What is the angular speed of the body when the plane of H is vertical? Oh, okay, okay, I understand what they're saying. Right. So, well, I mean, it's just rotating. What you could do, I mean, energy conservation, right, and get it done. Of course, it's like half I omega squared about this axis. That should be equal to whatever initial potential energy it have. Okay, no, the final potential energy has to be like hard to figure out and whatnot. So maybe just integrate it directly. So you got this kind of thing. So if say it's theta, right? So this h is making theta with the x-axis or whatever. You got gravity over here. This, let's just say this is L. Yeah, all three of these are just L, right? Okay, and masses. Ah, I didn't give anything. Well, these are identical, so maybe that's all we need. I don't know. So the force on this whole thing, that's just going to be, yeah, right. That should be the thing, of course. That's how we do it all of the time. All of the time. Yeah, that's the thing. Hey, wait. Should we take this into the system or not? That's confusing. I mean, if this is not going to rotate, why even take this? Because like this guy's inertia is not being counted anyway. And then, huh? That's not good. Should we take that into account? I mean, if this was okay, this is a very weird thing. I mean, should we take this or not? Doing just for that, it will be like 2 mg. So 2 mg force. Oh yeah, the center of mass will change. Of course. So then you have to take this because that will be making it easier to do everything, right? So if you do take this, then it's just going to be on L upon 2, and that's why mg L upon 2. But you have to take a component. So this angle is theta. This angle should also be theta, I guess. It's gonna be 90 degrees and everything. But this angle is uh, theta right there. So this should be theta. Yes. So yeah, cosine theta. That's our torque on this thing. That upon the inertia. So inertia of this whole thing. Well, this doesn't have any inertia because it's about that axis. And then you got this guy, so it's just ml squared. Oh, it should be 2 mg. Because you're taking each of these 3 mg. Because 3 of the see. Okay, and then you got ml squared upon 3 for this guy. And what about this guy? Well, it's at L's constantly, so it's gonna be ml squared, just like that. I guess that's correct. And then for this is it just has 0. M cancels, L cancels. L upon 3 plus L is 4/3. Goes on top 9 upon. Oh, you can just take 8. So 9 upon 8. You got G cosine theta upon L. So that is our angular acceleration, I guess. And now I just need to integrate this with theta, right? Changing. Ooh. Oh, we just want what? The angular speed. Of course, you can write this as omega d omega. What am I writing? Omega d omega upon d theta, right? And then integrate. So from theta is equal to 0 to pi upon 2. And in omega initially is just 0. So it's like omega squared. And that 2 cancels with this thing. So I'm going to make this 4, 9 upon 4, g upon l. And the cosine theta goes from, the integration of that. So sine theta, it goes from theta equal to 0 to theta equal to pi upon 2. So it's going to be 1, just like that. And then there we go. So 9/4 of g upon l, that's our omega squared. So omega angle also is just 3 upon 2 square root of g upon l. Make sense? Wait, is that? Oh, I think that's for some other question. Yeah, fourth. So it's going to be 3 upon 2 square root of g upon l. Fourth done. Okay, fifth. Get deleted. Fifth is a solid cylinder of mass something, radius something, pivoted at its center and three particles of mass mounted at its perimeter as shown. The system is originally at rest. Find the angular speed of the cylinder when it has swung through 90 degree anti-clockwise direction. Uh, okay. Wait, I don't understand what's happening. Pivoted at its center, three particles of given mass mounted at its perimeter. Okay, system is originally at rest. Fine. Find the direction of the and okay, find the angular speed of the center, but it has swung through 90 degree in anti-clockwise. Wait, but in under what condition? What's the torque? Come on, give us something. Uh, no, it doesn't make any sense. Unless you state what's happening actually, I cannot solve it. Okay, we'll have to go with some assumptions. Maybe it's a vertical scenarios like this is in the vertical plane, something like that. Because if you gave nothing, there's only one thing I can do. Assume it's in under gravity and then do it. So originally at rest. Okay, I understand this. Okay, cool. So I think what's probably happening is like, wait. It originally is at rest. Huh? Um. Okay, you know what? Let's leave this because I'm not clear what these people are trying to find. I think what they are trying to say is sorry, we got this cylinder like this, and we got these three particles on top first of all, so that's our unstable equilibrium, and then this. Come on, please don't disturb me. And then this comes going down, yeah, and then this goes down and it goes 90 degree anti-clockwise, so now it becomes this as they have shown, right? So they want to find the angular speed of the cylinder. Of course, I mean, let's just do energy conservation and get it done, right? Half I omega squared is equal to our change in mgh. So this will be easy because these two have now the same energy, potential energy, gravitational potential energy, and this guy just went down. So if these are of all masses m, and this complete cylinder is of mass capital M, right? So you would say, okay, mgr, I guess, because radius, that would be equal to half I omega squared. So half our inertia. So this cylinder is like hollow or what? Solid cylinder. Oh yeah. So it's a completely filled, and that would just mean mr squared upon 2 is the inertia. And then each of these just has mr squared, it's like 3 mr squared. Okay, this thing times omega squared, right? That should be the thing. Oof, I guess that works. Okay, and now we can solve this. They gave capital M and small m as well, right? This cancels, this cancels, this cancels. It just becomes, or you can write this as 4 capital, no, it's going to be small m g upon, just delete off this. So 4 mg, okay, and then upon 6m times, 6m plus just capital M, right? And all of that times R. Yes, and the square root of this thing, that will be our omega. So that's like 2 square root of m upon 6m plus m and all of that times g upon r, right? That should do it. So that's fifth. I don't know, this is coming with the assumption that it's in the vertical plane. It's, you know, just under influence of gravity and the normal force and whatever at this pivot point. I don't know. Right, now what do we want? Yeah, just plug values in it. So 2 square root of the mass, and small m is just 0.1, right? And capital M is 1. So I will take this as the ratio will be 10. So 1 upon 6 plus 10, that should do it. And then G upon R. So G we don't know right away. R is 0.5. Okay, so I'll just take G to be 10, and that upon 0.5 is going to be 1 upon 2. This thing is just going to be 16, so 16 upon 2 is like 8. I think I should take 9.8, because yeah, I could take 9.8. Oof. Oh, come on. You could take 10 or you could take 9.8. I'll just take 10. Who cares? It's gonna be 2 square root of 80. Yeah? 2 square root of 80. So that will be 8 square root of, 80 can be written as, or just not go that way. So 2 times 4, because 16 times 5. So 2 into 5 square root of 5. Yes, this will be just 8 square root of 5. Okay, next, sixth question. A rod of length something, mass something, free to rotate about a horizontal axis, passing through a hinge P in the figure. What? Okay, hinge P, some rod of length R. Which rod? This rod, mass M, is free to rotate about a horizontal axis. Okay. First, it is taken aside such that it becomes horizontal and then released at the lowest point. The rod hits the block P with of mass M and stops. Oh, so it's just a momentum transfer. Fine. Find the ratio of the masses such that the block P completes the circular track of radius R. Neglect any friction. Well, we could do just angular momentum conservation, right? Yeah. So whenever it will hit it, whatever angular momentum must be going on with, same thing is just put on to this small m. What we want is find ratio of masses such that the block B completes the circular track. So you want minimum ratio or just ratio? It could be doing it for multiple different ratios. Yeah. What if this guy is like really small or something? You're not even saying it's some kind of collision, it's elastic or something. No, you're saying it stops, right? It could. Yeah. Multiple possibilities for that. Okay. I'm sure they're talking about minimum ratio, but fine, let's just do it. Just analyze. So when it comes down, what will be the angular velocity? It's gonna be half I omega square. It's like, okay, let's just do it. This guy's center of mass is over here, and then when it comes down, it goes over here. So it's L upon 2 that it goes down, right? So mg L upon 2 is equal to half I. So I is to be ml squared upon 3 times omega squared. Or you could use angular momentum directly. Yeah, angular momentum would just be inertia times omega. So yeah, why not? So half I omega squared, write that as angular momentum, which I already use L. Let's use small l for that in that case. So then this will be angular momentum squared upon inertia, which is just ml squared upon 3. Yes. So that means angular momentum squared is equal to m squared gl cube upon 3. Now that just means angular momentum is going to be ml square root of gl upon 3. Okay, now what we do is give away this whole angular momentum to this guy. So this is going to be equal to m times whatever velocity this guy gains, and that times this length, so L, that should do it. So there we go, some stuff gets cancelled. So let's say small m upon capital M is the ratio we are looking for. Oh, so they want the ratio of masses, but what is to what? This is so terribly written. I'm just gonna say m upon m is equal to eta and then solve. So eta times v is equal to square root of gl upon 3, right? Well, yeah. So we got what the velocity is going to be. Now, since we want this guy to complete this circle, right? Complete the circular track of radius r. So when it's at the topmost point, the thing is mg squared upon r. That's centripetal acceleration is just provided by the gravitation. So g is equal to v squared upon r, right? So I could say, okay, v squared is equal to gr. This v is different from that v, okay? So that would be equal to, and like v squared is equal to u squared plus 2as. So this would be equal to whatever velocity we had over here. Oh, we have to just use v final and then v initial over here. The v initial is what v this was, and then this thing squared plus 2 times of as, which is, oh, it's gonna be negative. It's gonna be negative. And yeah, well, right. It is definitely gr. Then you got this is equal to v squared minus what's I doing? Oh yeah, 2gr plus 2r times g. Oh, that times 2 once again. So 4gr. So v should just be equal to square root of 5gr, but then v is equal to this. So, oh, and by the way, r is just L in this case. So what do we make of it? That, yeah, v is just equal to this thing, right? So you can say 1 upon eta square root 3, that should be equal to square root of 5. So that eta, I mean, we know this is the minimum condition thing, right? It's the minimum velocity that this should have. Even if it has more velocity, it will still work. Yeah, so if your small m is smaller, then it will work because it will have higher velocity. And I guess that's how it should be. So eta minimum would just be 1 upon square root 15. Right? That's my answer. 1 upon square root 15. Okay. Minimum is equal to 1 upon square root 15. Well, good thing it's subjective, or this would be impossible to answer. 6 kg carriage is supported as shown by 2 uniform discs, each having a mass of 4 kg and a radius of 75 millimeter. What? So these two discs, okay. Knowing that the carriage is initially at rest, determine the velocity of carriage 2.5 seconds after 10 Newton force has been applied. Wait, what? Oh, so just going yeah, okay. Understanding. And is this on, what kind of surface is this on? Rough surface, I guess. Oh yeah, so they roll without sliding. Good. That's what we had to know. Okay. So whatever velocity this carriage is going with, these discs are going with half that velocity, right? And then you got this force acting on this whole thing, okay? And you give us the time required, okay. There's gonna be friction as well. That's just really not good. Friction. Okay, let's instead of that. Okay, first of all, we know that A and B both should go with the same angular velocity, otherwise it wouldn't make sense. One would be very fast and slow. Yeah. So according to that, the forces, I mean, the angular acceleration must also be the same. So the friction forces on both A and B, those must be the same. So let's say those are, I don't know, F. Then just have F upon 2R. So R is the radius of these discs. And these are discs, right? Okay, cool. So, sorry, F times, what am I doing? I have to write dot. What am I doing? So 2FR upon the inertia about this contact point, which is mr squared upon 2 plus mr squared, like 3 by 2 mr squared. This thing is equal to our angular acceleration, right? Okay, cool. What we are looking for is this thing times 2r, because that will be the acceleration of this guy, I guess. Yeah. So 2 times of this thing, also that times r, in fact. So this will be, that's 4, right, already. So 8f upon 3m. Yes. Yeah, that should be the thing. Okay, this is equal to the acceleration of this carriage. and that's also equal to this force minus the frictional force, which is 2F on this guy, and all of that upon the mass. So call this thing capital M, right? So from here you can figure out what the frictional force is at different moments. Yes, they also didn't give anything about the coefficient, and also they said this roll without sliding on both surfaces, I guess. That would mean, yeah, yes, assume friction is always sufficient. Okay, now what do we do? Uh, yeah, they gave after what time? So fine, it's doable, right? Velocity of the carriage, 2.5 seconds after the 10 Newton force being applied, and this is equal to the acceleration of this carriage. Cool. Just solve for f, get the acceleration as a function of time. It's gonna be constant anyway, so yeah, this will work. Oh yeah, I mean this was actually very easy because what we can do is just write this as 2f and then you got 3/4 m, and then we just use 10 equal ratios and get it done. So 10 upon m plus 3/4 m. That's equal to our acceleration. Cool. Okay, so now what? Yeah, we just want the velocity after 10 seconds. It's gonna be 10 times of this thing. So 100 upon capital M plus 3/4 of small m, which is 100 upon. In fact, it's write it in the the usual format. So instead of writing 10, we'll just write f. Okay, it will be f upon f times t. So f times t upon capital M plus 3/4 of m. That would be your answer, right? This will be our answer, but in this case, it's a value. Its value is, so force is just 10, time required is 10, mass is, oh, also the radius. I mean, okay, wait, what? We didn't even use the radius. Wait, seriously, what? We didn't even use the radius. Did you see that? Huh, that got cancelled. Just like that. This was perfect. Yeah, this is just perfect. Anyway, the thing is going to be 10 times 10 upon capital M is just 6 kg, and then you got plus 3/4 of small m, because there's like two of these. Huh. So it is, yeah, 4 kg. So each of them has 4 kg. That's what we want. So it's going to be 3, just like that. It's going to be 100 upon 9, which is 1. So 11.11 whatever. So 1 bigger. That should do it. Let's go to 8. A bar of mass m is held as shown between 4 discs, each of mass m dash and radius r is equal to 75 millimeter. Okay, oh, it's like this thing, but different. Determine the acceleration of the bar immediately after it has been released from rest, knowing that the normal forces exerted on the disc are sufficient to prevent any slipping in. Assuming that, oh, so they gave us the masses, the mass m dash of the discs is negligible. What? Oh, so these are different situations, not all of them simultaneously. Fine. What we want is just the acceleration of the bar immediately, right? Okay, cool. Right, just write the angular acceleration of these guys. So just like previous, and these are rotating about the center, I think. Yeah, these should be rotating about the center. What else could we possibly have? Yeah, whatever. I'm gonna assume it, these are about the center. Fine. And what that means is, if the friction force from each of these is, let's say, F, is this even correct to assume that? Yeah, it is, because each of them will be accelerating, angular acceleration will be the same for each of these. So the friction force will be the same applied on these guys, these discs. That's why friction force on this part on each of these will be the same. So F times 2r upon mr squared upon 2, right? Uniform discs. Yes, mr squared upon 2. But 2 times r of that guy. Yeah, because we want. Wait, no, that's not correct. Sorry. It should be fr upon mr squared upon 2. Yes, and that times of r. Sorry, this should be the correct thing. Makes sense. Because about the center, right? Okay, and Now this is our angular, sorry, this is the actual acceleration, not the angular acceleration of this guy. So we can also write this thing as the gravity acting on this. So it's going to be G and minus the frictional acceleration. It's going to be 4F upon capital M. That should do it. This cancels. All you just get is like 2F upon M is equal to G minus 4F upon capital M. So, and this is equal to the acceleration. What we want is acceleration of the bar immediately, right? So we just want this quantity. Cool. Well, what I'm thinking is let's just do capital M times A. That is going to be M capital M G minus 4F, and let's also do small m times A, but 2 times of that. So small m, 2 small m A is equal to just 2F. Yeah. So sorry, 4F. And then let's add these. So that will be capital M plus 2 small m times A is equal to all that. Yeah. So acceleration is just going to be mg upon capital M plus 2 small m. Cool. And now return to their notation. So our acceleration is going to be, so according to them, the bar is of mass small m, and these disks are of mass m dash. So it's going to be like this. Okay, so let's do the cases. Radius once again wasn't really required. So mass given, okay, m and m dash, if these are these things, okay. Right. So this will just be equal to 5 upon 5 plus 4, which is 5 9th of G. I'm going to leave it like that. B is, it's looking really ugly. Okay, B is the mass m dash of the disk is negligible, then this thing is going to be negligible, so it's got G. As expected. C, the mass m of the bar is negligible. Wait, what? Are you serious? Then this acceleration is going to be infinity. Wait, no, that's, no, something's wrong. Wait, what? But then it's like 0G upon, oh yeah, acceleration is 0. That's more like it. This will be 0, this will be 0, so 0. Yes. I'm thinking of something else completely. So yeah, this will be 0 as expected, because these disks just won't let it go. Okay, that's awesome. So to 9th. Why can't I scroll down? Oh, okay, sorry. Fine. 9th question. Determine the point of the rod AB of length 0.9 meter at which the force P should be applied if the acceleration of point B is to be 0. So point B is to be, this guy's acceleration is to be 0. Point of AB of length 0.9 whatever. Force P should be applied. Knowing at magnitude of P, oh, so P is a force, 2.7. Okay. Determine the corresponding angular acceleration of the rod and acceleration of the center of rod. Mass of rod is 1.5 kg. So just at this moment, right? I guess. Force P is to be applied perpendicular to the rod, and the rod is in horizontal smooth plane. Cool. Hey, I've seen this somewhere before, whatever. So let's say it's x from the center of mass, right? And you got, let's not use P, that's really bad. Let's use F. And this whole length will be all just L. Yeah, so what we want is, first of all, okay, I mean everything. Angular acceleration, the acceleration. Oh, and you basically want the acceleration of B to be 0. That's our main condition, right? So this guy should have 0 acceleration. Wait. If that has 0 acceleration, we can just take, oh yeah, why not just take the whole system as seen by this point, so right above B. According to this guy, the inertia of this whole thing is not changing, right? So yeah, why not? Of course, this will be really awesome, right? Then okay, that just means x plus L upon 2 times F. In fact, let's just say this whole thing is x. So x times f upon ml squared upon 3. That's our angular acceleration, and that's also equal to angular acceleration seen in the center of mass. But there's no force on this guy really. Yeah, so it's just going to be f times of x minus l upon 2. That upon ml squared upon 12, I guess. Yeah, this is our equation. So this cancels, perfect. Everything is good. And then 3 over here. Oh, this also cancels with 4. 4 goes on top, it becomes x is equal to 4x minus 2l. So 3x is equal to 2l, x should be 2l upon 3. Now we know where to apply the force. And they also want the angular acceleration. So just this whole quantity, in fact, so x times f. So 2l upon 3 times f upon ml squared upon 3, I guess. I'm going to use small l squared upon 3. And this cancels, just get this guy. 2f1 ml. Yeah, that's our angular acceleration. What they want is, no, so they want the acceleration of the center of rod. Just multiplies by L upon 2, right? So you got 2F upon ml, that times L. So 2F upon N. That should do it. Wait, what? Okay, that doesn't make, sorry, times L upon. Of course, it's only F upon M, as expected. Wait, corresponding angular, oh yeah, so angular acceleration we know. Angular acceleration would just be 2F upon ml. Our acceleration would just be so as acceleration of the center of mass, F upon M, as expected. And now we know what x is. And that's why this works out. Yeah. Okay, cool. Let's submit this as an answer. Okay, so 2L upon 3 from B. Okay, and angular acceleration, just put that in there. So 2F upon ml, and acceleration is just equal to F upon M. Have space. Acceleration is equal to F upon M. Calculate this guy. They gave us the thing, right? So force is, the force is where it go, 2.7, and then M is, mass of the rod is 1 kg, so it's just 2.7 upon 1.5. It's like 27 upon 15, that's 9 upon 5. So that's going to be 90 upon, 18 upon 10, 1.8 meter per second square. And then you want 2f1 ml, just do like this thing upon L upon 2, that should do it. So 1 upon 8 upon, so 1.8 upon L upon 2, which is, so the length of the rod is, where it go, 0.9, and I think upon 2, that should be the thing. So this is going to be 4, perfect. This is going to be equal to 4. Okay, and then 2L upon 3 is, I won't even do it, okay? I won't even, yeah, next. Uniform slender bar AB of mass M is suspended from two spring restraint. If the spring 2 breaks, determine at that instant. So, okay, spring 2 breaks. Yeah, I mean the extension is not changing instantaneously, and that's why same. I mean that force is kind of same. It's still the same. So just figure out that force. You know what this force is? Oh yeah, that's how it's going to be. Or you could do this thing. I mean, you know that right now it's all of it is just in equilibrium. When this breaks, this F2 force is now not there. What you could do is add add a pair of forces. So F2 in this direction and F2 in that direction. So opposite, and that's why they cancel. It works out. And now that whole assembly of F2, F1, and whatever this gravity forces, that's 0, and this F2 is the negative F2 thing is now in this direction. So you can do that. Right, so this will be really nice. I mean, yeah, it works out. Okay, so if spring 2 breaks, determine at that instant the angular acceleration of the bar. Yeah, first of all, figure out what the forces should be. So let's just say both of these, I mean, we know both of these are going to be the same forces. It's going to be like 2f cosine of 60 degrees, so it's just going to be f is equal to mg. Wow, that was fast. That was fast. And yeah, the angular acceleration will just be mg upon L upon 2 and yeah, times all that stuff, right? Okay, is this correct? It must be, right? That's cosine 60 degrees over here. Yeah. Oh no, it should be mg upon 2 over here because it's yeah. Okay, understandable. Right, that will give us the thing. And you also want the acceleration of point A. Well, it's going in this direction as well as in that direction. So, yeah. Oof. Some upward component, some component in this direction, as well as some component in that direction. Because the acceleration of point. Okay, we'll have to figure out the acceleration as a vector as well. Okay, let's do it. So what I'm saying is this guy has force, net force, um, mg upon 2 in this direction, and this what some of the stuff. It's going to be mg times square root 3 upon 2 in this direction. So that means this whole bar, this guy's center of mass has g square root 3 upon 2 in this direction, acceleration, and g upon 2 in this direction. And this guy, so what's our angular acceleration? Angular acceleration will just be equal to mg upon 2 times L upon 2 and that upon ml squared upon 12. Yes, cancels. Wow, very weird. Okay, L cancels. 12 goes on the top. 6g upon what am I doing? That's 2 over here as well. Actually, it should be in that case 3g. So 3g upon L. That's the thing, huh? So angular acceleration is 3g upon L. So this guy's acceleration, relative acceleration, that will just be L upon 2 times this guy. So it's going to be 3g upon 2 in this direction. Well, guess what? That just means, okay, this is going g by 2 down, but then it's going 3g upon 2 up, as seen by this guy. So just add these up. It should be just g upwards. So this point A is g upwards, and g square root 3 upon 2 in this direction. Yes. Oh, that is wow. And they want the acceleration of point A as a vector or what? Oh yeah, as a vector because they gave us x and y. Perfect. So angular acceleration of point A, that will just be g times square root 3 upon 2i plus plus j, just like that. Yes, and acceleration of B, that's really different, I guess. So this has 3g upon 2 in this direction. So that's going to be 2g in the minus j direction. Yes. So it will be g times square root 3 upon 2 I and then minus 2j. Yes, that should do it. And our angular acceleration will go. So that's it. That's the answer. Just copy these. Yeah. Okay, 11th. 11th is a double pulley is attached to a slider block by a pin at D. What? Slider block? What slider block? 2 centimeter radius inner pulley is rigidly attached by the outer pulley. Inner pulley and then you got an outer. What is a slider block? By a pin at D. Double pulley. Oh, so this is okay. So this A and B, this thing is a double pulley and attached to a slider block. So this is a so this is the block they're talking about. Huh. Oh, okay. So you got like thread attached like, and then it's going like that. So from D you have a thread going up, and then from this A point you have thread going down, and then all of this assembly, it's just yeah, this whole thing is attached to this rectangular slab or whatever this thing is, right? And that's between these two walls. What kind of thing is this? Okay, so that's why it's ladder block because it slides, I guess. Okay, the 2 centimeter radius inner pulley is rigidly attached to 4 centimeter radius outer pulley. This is 2 centimeter, that's 4 centimeter. Knowing that each of the two cords is pulled at constant speed, 12 centimeter per second, as shown. It's pulled at a constant. Determine its center of rotation of. So the rate of pulling is like the rate of increase of the length outside of the pulley, right? Yeah, that should be the thing, I guess. Hmm. So you want first of all the instantaneous center of rotation of the double pulley. What? Oh, okay. Okay, understandable. But then this thing is also going up, I guess. Yeah. Huh. So this is 12 centimeters per second. Oh, what is this? Wait, are these B and A things rotating differently or with the same angular velocity? So center of rotation will be double pulley. I guess yeah, both of these must be rotating the same angular velocity. That probably makes sense. So you got V going up, and then this is what is this? Oh, well, think about it. This is like V going up, omega r in this direction, so omega r minus V. That is the velocity of this, like the parts of this string. So that's also the rate at which new string is being formed, right? That probably makes sense. So yeah, omega times r. So let's just use small and capital R to mean this radius and that radius. So this will be omega times small r minus whatever velocity this guy has. So, what was I doing? And this thing is going up, then omega r. That's why this is going down. Yeah, I guess that makes sense. What if this was opposite and wait, shouldn't this going up actually help in creating more length? Yeah. Oh, yeah. Okay, wait. But clearly, I mean, the string's velocity is just that, right? It has to be. Oh, so this string's velocity is given. I understand that. So let's say we talk about time delta t. In that, so you got this string. So this particle of the string would have gone down by omega r minus v, but then this whole pulley would have gone up by v. So let in time 1 second, I don't know, right? Delta t, just add that in there. So the whole string that got created would just be omega r times delta t, and that's why the rate of increase of the string outside is just going to be omega r. Yeah. And similarly, we could do the same thing for this guy as well. So it's going to be omega capital R. Yeah, of course. That should make perfect sense. So, what do you think? Like both of these things are the same. Wait, but oh, so the double pulley does go in different angular velocities, I guess. This is unexpected. Uh, yeah. What do we do now? Oh, okay. Wait. It is pulled at a constant speed. Oh, not that it is right. So it's not just the increase in the length of the string outside of the pulley. No. It's being pulled up. So if for example you have, I don't know, this is where it's being pulled from. Okay, and we know like this string just has omega capital R plus v as the velocity. So in delta t time it will go, I don't know, here, and this whole level would have gone up by v delta t. So it did create new length of omega capital R, right? But the thing is, like, this went up, so this would also go up by omega r plus v times delta t, and that means omega r plus v would really be the rate of increase of, sorry, rate of it being pulled up, right? Not increase of the length, but it being pulled up. Makes sense? Yes. Oh, now we can do it. Omega r minus v is equal to, oof, yeah, that's the thing. Of course, that's how it should be. So that will be 12, and whatever this is going to be, call this thing as A, where A is the 12 centimeter per second thing. Okay. Omega capital R plus V is also equal to A. So what now we want is the instantaneous center of the rotation of double pulley. Okay, so that just helps us in finding what omega is, right, from this thing. So V is unknown, omega is unknown, right? We can figure out what these should be. Velocity style of the title block. Of course, we can do it. So V is equal to A times of 1 upon capital R minus 1 upon small r. Oh, sorry. That's wrong. That's wrong. That's really wrong. Sorry. uh, V times of 1 upon capital R minus 1 upon small r is equal to A times of plus right there. Subtraction. That's how it should be. 1 upon capital R minus 1 upon small r. Yes. That's unexpected. Because clearly omega times small r, that should be, yeah, I mean, like, this thing should be a bigger quantity, but it's not. Oh, something's not right about this. How could this be? The only way this can happen is like this block is going, yeah, it must be going down. That's what must be happening. So that this actually happens. Of course, it's the only way it's possible. So velocity is in fact negative. Okay, so this is like V times of small r plus capital R is equal to A times of small r minus capital R. So the velocity is just A times small r minus capital R upon small r plus capital R. And you can figure out omega, so subtraction. Oh wait, what? No, not subtraction, addition. So omega is equal to 2A upon small r plus capital R. So what, where we're supposed to find? We're supposed to find the instantaneous center of rotation of the double pulley. So this pulley is rotating with angular velocity like this, and then it's going down by this by velocity A times of capital R minus small r upon capital R plus small r. Yeah. From this we want to find the center of instantaneous center of rotation, of course. So for that, so a point that is stationary, if the whole world was rotating like that, yes, that would be same thing as saying, okay, V, and so let's say it's X in this direction, but omega is, oh, it's gonna be in this direction, right? Yeah, well, V is in that direction. I just gonna use this thing actually. Write down everything neatly. Okay, now we are ready. So what we would want is what velocity in this direction. The angular velocity is like this. So over here you might have a point. Relative velocity like this, but then velocity like that, and this should match up so that it becomes stationary. So if this thing is X, then what we want is like V is equal to omega X. So X should just be V upon omega. So division of this should be, that's capital R, sorry. Oof. So that A upon capital R plus small r cancels. Just get this thing. Right. So that will be this much towards right. Now we can do it. Per second. Wait, what? The length of cord wrapped or unwrapped on each pulley per second. Oh yeah, okay, that's what we were talking about. The length of the increase of, sorry, the rate of increase of the length of the cord, which would just be omega small r, omega capital R. Yes. So let's start answering. A. Density near center of rotation of the ball pulley. It's going to be capital R minus small r upon 2 to the right of B. Yes? This is a needed anymore. B. Velocity of the slider block. So V is equal to A times capital R minus small r upon capital R plus small r downwards. Okay, cool. C. Length of the cord wrapped or unwrapped. So this is going to be this times, first of all, so like for the pulley A, this will be, wait, okay, so this pulley, no, call it as A. So A will just be omega times small r. So 2A small r upon small r plus capital R. And then B will be 2A capital R upon small r plus capital R, right? Okay, that's cool. Let's actually calculate this thing. So first of all, A is just 12 centimeter per second. What's this thing, this ratio, capital R minus small r, all that stuff? So inner radius is 2 centimeter, outer is 4, so it's like 2 minus 1 upon 2 plus 1, that's going to be 1/3. So 1/3 of 12 is 4, so it's going to be 4 centimeter per second. Yeah. A. So small r upon capital R plus small r, that's going to be 1 upon 1 plus 2. Yes. So so 2/3 of A, in fact, which is like 4, but 2 times of that. 8. Yes. 8 centimeter per second. And for B, it will be capital is just 2 times of that. It's just 16 centimeter per second. Yes. So to 12. The end B of rod AB, which makes angle theta with the floor, is being pulled with velocity V naught as shown. Taking the length of the rod as L, calculate the following at the instant when theta is equal to 37 degree. The velocity of rod A, what? Velocity of end A. This thing is being pulled like that. You want to find the velocity of A. Well, it's gonna go down. That's only way it can go. Angular velocity of the rod. Velocity of the center of what? Center of mass of the rod. Fine. Angular velocity is not that hard, I guess. But once you know what the velocity of the center of mass of rod is, it will be a piece of cake. Fine. So, what angle was this? Theta with floor. Now this is going like that, V naught, and let's say it's going down with V. So this component will be, this is also theta, right? It's going to be V naught cosine theta. This should also have the same component, but this is now 90 minus theta, and that means this should be V naught cosine theta upon sine theta. Yeah. Alright, so V naught cot theta. Okay, then this center of mass guy, it just has like m times this, m times that, half of, sorry, upon 2m. So, oh wait, that's different. Sorry, center of mass. But we know like this is going to be the midpoint of these two all of the time. So, might as well just do that, huh? Does it really matter? It's going to be like that, of course. Yeah, there we go. So this just has V naught upon 2 in this direction, and oops, like that. And then V naught cot theta upon 2 in that direction too. And what the angular velocity should be. So as seen by center of mass, this guy has got V naught upon 2 in this direction, and V naught cot theta upon 2 in that direction, where this angle is of course just theta, right? Well, think about it. If I arrange this correctly, it's going to be V naught upon 2, and that's going to be V naught upon 2 times cot theta. Then this angle must have been theta, so that tan theta of this thing would be this. So it's going to be 90 minus theta right here. Whatever this, yeah, it's going to be 90 minus theta here. So this must be 90 degrees, of course. And the magnitude of this velocity, what will that be? Oh yeah, what will that be? What was it to be? Sorry. Square root of that plus 1. Of course, cosec theta. So V naught upon 2 cosec theta, that's the thing. The angular velocity will just be V naught upon 2 cosec theta, but that upon L upon 2, of course. So that's going to be this thing upon L. Does that make sense? Right. You can figure out everything now. Okay. Let's just put down the answers. Velocity of the end A. So just write it in vector form. Small a. Velocity of end A. So for this guy, right? No, for this guy. Sorry. We could just do it, you know. Oh, come on. Let's just write the magnitudes. Who cares? It's only V naught cot theta. Okay, B. Angular velocity of the rod. We already got this thing. V naught upon L sine theta. Let's do C. Velocity of center of mass of the rod. So this length is like V naught upon 2 cosec theta, and that's why V naught upon 2 sine theta now. That should do it. Okay. 13th. Am I going too slow? I guess. A rough flank of mass something placed on a rough what hollow cylinder of mass capital M. Plank cylinder. A constant force F making angle theta with the horizontal plank. Plank is also horizontal always. Okay, force making angle. Apply to the plank. Assume no slipping anywhere. Find the acceleration of the plank. Acceleration of the cylinder. No slipping. Okay. Acceleration of the cylinder and friction force at A and B. And just point in that point. What is this? Why? This is so repetitive. Fine. You got just like this plank has a friction force in that direction. You got this. Sorry, a force in that direction. You got this friction. And it always says what? It stays horizontal. Are you kidding? Huh. So horizontal always. Oh, okay, I understand. So first of all, I mean, like, I know friction is just going to be in this direction. What must be happening is that the gravity force is cancelling up the torques and stuff, right? And yeah, it must be such that this always stays horizontal. So we can just forget about the vertical balance and only think about the horizontal balance, because gravity cannot interfere with that. There's only friction force. And of course, friction force is completely horizontal in this case. So on B, that is. So for this plank, friction force is like to the left, and you got F cosine theta to the right, balanced up. So B is having F cosine theta acting on it, right? That's the friction force. So then we just want to find the friction force at A. So B is doable, right? So friction force at B is equal to F cosine theta. Okay. Friction force at A we don't know. Also, we want to find the acceleration of the cylinder. Okay, fine, let's do it. Angular acceleration, that's going to be this friction force like F cosine theta. That times. Wait, is this what kind of thing is this? It's the hollow cylinder. Oh, yeah. Hollow cylinder. That's going to be mr squared is the inertia. So F cosine theta times 2r upon mr squared. That is our angular acceleration. That should be equal to. So for the center of mass, that would just be FB, which is this guy, but that times R and minus. Oh, sorry, it should be 2 mr squared because mr squared about center of mass and then mr squared because of parallel axis. So F cosine theta r minus the, oh, it should be, let's just say the FA thing is positive in the right direction. So then it will be negative over here. It's gonna be F A, this is called F for now, FR, and that upon just MR squared, yes. That's how it's gonna be. So okay, cool. It's like FR cosine theta is equal to FR cosine theta minus. Does that mean oh yeah, so it's just rotating by itself, huh? It's just rolling by itself. Wow. You don't need any friction force. Wow, this is unexpected. But hey, that's what it is. So F cosine theta upon m is that acceleration, but then F cosine theta times r upon mr. So it's like F cosine theta upon mr, but that times r is like F cosine theta upon m. That will be the relative acceleration. So yeah, it somehow turns out to be 0. Perfect. So A, there is no friction. Nice. And then also we just want the angular acceleration. Just the acceleration. And that's gonna be easy. There was no friction force. So it's just F cosine theta upon the mass. Okay, 14th. Two particles of masses 7m and 3m are fastened to the ends A and B respectively of a weightless rigid rod. So 7m and 3m, which is freely hinged at point O, 3 feet from A. So this is like 3 feet. I'm gonna call it 3x, I don't know. If the rod is just disturbed from its position of unstable equilibrium. Unstable. Oh yes, like this guy. Okay. So it's hinged. I guess this is not moving on. Yeah. Just got A over here, got B over here. That's 7m. This is 3m. Some distance. Okay. I don't know, call this thing like X and Y. Who cares? Okay, if the rod is disturbed from its position of unstable equilibrium. Wait. Is that the... Yeah, that must be the unstable equilibrium because the... Of course, that has the thing, right? Find the velocity at which A will... Oh, it's 15 feet long, huh? And this is 5 feet from... Wait, what? 5 feet from A. So is this the unstable equilibrium or that? Oh, we have to do some stuff. So this 5 thing is 10. Like 5 times 7 is 35. This thing is going to be 10 times... Oh god. So is 35 minus 30 bigger or 30 minus 30? Of course 35 minus 30. And that means this thing will be the unstable equilibrium, right? Yeah, that's how it's going to be. So this really is the unstable equilibrium, huh? Okay, find the velocity at which A will pass through its position of stable equilibrium. Right, so just find the angular velocity. Come on, it's just energy equations, right? Yeah, right. So just the gravity doing work because this guy doesn't do anything. Assume friction, no friction. Do we have to? Okay, they didn't say anything about it. Freely hinged. I guess that means no friction or whatever. Fine, we'll say no friction, and let's just do it. So, I mean it's gonna be 35. That's like feet. I'm gonna use X for that, right? Yeah. So going from 5mx, sorry, 5mgx to now minus 5mgx, that will be 10mgx of energy provided. That's going to be equal to half I omega squared. So I is just like this guy mass is squared. Whatever. So 7 times 25 plus 3 times of 100. Perfect. It's going to be 25 times 7 plus 12, which is 25 times 19. That's weird. 25 times 19, huh? Wait, what? It really is like that. Okay, okay. Let's be bit fine. Yeah. The quantity is half I was like, okay, that's the inertia. This is the inertia. Mr squared, mx squared, and that times omega squared. So mx squared omega squared. What we really wish to find is omega times 5x, right? So look at this. Isn't this nice? Half into 19 into m into 5 omega x. That guy squares whatever velocity it had. Right. That's going to be equal to this thing. So this cancels. Yeah, that's like 20 upon 19. Gx is equal to, well, v squared. Ha. Isn't that right? I guess. Hmm. That should do it. So really, I mean, like v is going to be square root of 20 upon 19 times gx. We know what x is, and then now we can solve it, of course. And since this is like so calculation based, I'm gonna not do a general form of these things. So 20 upon 19, g will just say it's 10, and then x is what is this guy's x? Oh yeah, 1 feet. What? I'm not what? Wait, that's just not good because feet is not SI. Oh, 1 feet is like what? 30 centimeter, I guess. Around 30 centimeter. It's like 0.3 meters. Sorry. Is that correct? Something's wrong. It's not 30 cent. It's like 12 inch. No, I don't remember what a feet was. What? Seriously. I can do all of this good physics and I don't remember what a feet was. Ah. But like, okay, a whole ruler is 30 centimeter and that's a feet. Isn't that correct? So it's supposed to be 0.3 meters. That's it. I'm gonna do that. So yeah, the square root of 20 times 3 is like square root of 60 upon 90. Yes, yes, approximately square root 6, but yeah, square root 60 upon 19. Yeah, in so meter per second. That should do it. Okay, cool. Next question. Let's go to 100 and what? Sorry, let's go to 15. Two steel balls of equal diameter are connected by a rigid bar of negligible weight as shown and are dropped in the horizontal position of from height h above the heavy steel and brass base plates. Steel brass plates, two steel balls of equal diameter connected by a rigid bar of negligible weight. Drops down. We want to find the angular velocity of the bar, of the bar immediately after rebound. Huh. Oh, so coefficient of resolution is given. Okay. Right. Okay, understandable. So we can figure out what the velocity should be, and then after collision, yeah. Okay, makes sense. Perfect sense. This was easy. This is going to be easy. Assuming that two impacts, come on, obvious. I mean, like that's obvious because it's horizontal and everything. So yeah. What velocity will it go with? That's gonna be square root of 2gh, of course. So square root of 2gh, that's this guy's velocity. Now, when it will go back, it's going to be 0.4 of that, right? No, that's for the brass guy. For 0.6 for steel guy. It's going to be 0.6 of this velocity and then 0.4 of that velocity. So of course the difference is just 0.2, and then that upon this whole length, that will be the angular velocity seen by this point, which is also the angular velocity in general because for every point is the same thing. Yeah, I mean for any 2 points. You get the idea. So it's going to be 0.2 and yeah, that whole thing, and that upon this guy's length. So this time 0.2 and that upon L. That should do it. Right. So 0.2 is just 1 upon 5, right? It's going to be square root of 2gh upon 5L, which is, let's calculate it. G is 10. Okay. H is 0.1, so it's going to be square root of just 2. Wait, why do that? We can just do 9.8, right? So it's going to be square root of 4 times 4.9, but that and 0.1. So like 0.49. That's going to be 2 times of 0.7. So it's like 1.4. 1.4 upon 5 times L. 5 times L is 1 meter. So that's going to be 5, of course. Perfect. That will be 0.28. So 0.28 is our answer in SI units. And what did we what were we asked? Angular velocity. So it's gonna be these many radians per second, and it's gonna leave it like that. 16. And I'm being slow. 500-gram block P rests on a horizontal friction table at distance 400 millimeters from a fixed pin O. Okay, like half a kg block P rests on frictionless horizontal table, distance 400. Wait, this is this figure not for that? The block is attached to a pin O. Oh, okay. So this horizontal table, we are taking the top view. The block is attached to a pin O by an elastic cord of constant K. Oh, come on. This is like a spring. Oh no. That's very weird. And of undeformed length 900 millimeter. If the block is set in motion perpendicularly, determine the speed in the beginning for which the distance from O to the block will reach the maximum. What? Speed in the beginning for which the distance from O to the block P will reach the maximum value of half. Okay, so 1.2 meters. The speed when OP is equal to 1.2 meter and the radius of curvature of the block when OP is equal to 1.2 meter. All right, it's gonna be tough. Something like SHN, but even weirder. So this tension force will only be directed to center. So we can always do angular velocity conservation. Yes. Uh, I mean, yeah. So velocity when this reaches 1.2 is very easy to figure out. But when, so at what condition will it reach it? So when will this be the maximum? Oof. Okay, okay, think about it. I can't think about it. Half kx squared is equal to half of no, no. It's got to be more than that. A centrifugal force over there. Its radial velocity is 0. Come on, let's just write down the equations in radial and tangential form, right? So yeah, this acceleration in the radial direction. I mean, it's ooh, we could do this. So yeah, we could use that thing. What was that? Come on, remember it. Remember this. It was like r double dot minus omega squared r, right? Yes. This times r hat squared r. Sorry. Okay. And then plus, so for the tangential acceleration, you had something like r alpha, and then you got this thing 2 omega r dot minus r, sorry, plus r alpha. That's like pseudo force. No, 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 no. It had to be positive. Yes, that's correct. That is correct. So over here, so that's the, what is this thing? This is the acceleration um, of, well, any body. Wait, okay, no charge. Sorry. Got to pick up this bit. Right. So this thing is just the total acceleration in the radial and tangential direction for any body, right? No matter what kind of motion it's going in. If it's 2D motion, it's this, right? That's the acceleration. So in this particular case, alpha is, well, not 0 necessarily, but then there's no tangential force. And then you got this like 2 omega r. That might be cancelling out, right? We don't know how that's happening. We don't even care about the angle really. So get rid of that thing. You got this omega squared r over here, which I don't know, and I have no idea about this. Oof. You will have to write down some good equations for it. You have to use that this is actually 0, right? You have to use that fact. How else are you going to do it? No, it's just not going to work that way. Okay, think about it. Okay, come on, come on, come on. Wait, first of all, when this like reaches this guy's natural length, this will start putting force on it. It's not going to be an impulsive force, right? Because this guy's extension right now is zero, and then right, it has some radial velocity, so it will go up really fast, and then it will just go down because yeah. But that's I mean that's not exactly impulsive, so it did take some time. It's not like all of that happened instantaneously, right? Okay, that's understandable. Oh, come on. What am I supposed to do now? You can use these equations, of course. Uh, okay, you got to qualify that stuff. Just write down some equations. So first of all, r double dot minus omega squared r is equal to this acceleration will just be the radial force on this guy. So that upon r, that upon m, which right, it's in the negative r hat direction from the negative k upon m. And that times the extension, which is just r minus L naught, right? Yes. So undeformed length, right? They gave us the L naught thing. Cool. That's understandable. That's one equation. We don't know what omega squared is yet. But what about this guy? We can use that, right? So, right. It just tells us that okay, 2 omega r dot is equal to negative r alpha. Okay. What we want is omega squared, not this thing. Come on, give us something. Alpha upon omega. Right, I mean it's zero. That's zero right there. So it's gonna be like okay, natural log of r squared, so something like that. As it goes from something to something, we don't know. I mean throughout this motion, right? This is happening. Throughout this motion, this is happening. Even though like okay, this equation is only going to happen for when this will become taut, right? Before that, it's not going to happen. But this equation, so this is going to happen all of the time, right? Because there's no tangential force, no matter what you do. So we can just do it directly. It's going to be 2 omega, and then you got r upon r naught. So r naught will be however much it was away. So that will be 400 millimeter, right? That will be your r naught value. Oh, natural log. Sorry. What am I doing? So 2 natural log of all that stuff. That's gonna be like okay, r upon r naught squared. That will be equal to negative over here. So it's gonna be reciprocal. Okay. Omega. But okay, we know what initially omega is. Finally, we answer this omega right there. Yeah, so omega upon omega naught power of negative 1. Omega naught is not that hard to do. It's just going to be b upon r naught, right? Okay, understandable. Right, so let's write this down. R squared is equal to r naught squared. Omega naught upon omega, so omega naught upon v upon r naught. Yes, r squared is just equal to r naught cube. Omega naught. Sorry, omega naught. What am I doing? This is really wrong. Sorry. Actually, omega naught here and omega over here, and r naught omega on r naught square omega naught. That will just be r naught b, and that upon omega. That should be doing it. So now you know what r squared is. Huh? Isn't this weird? Because like first if we just go like that, and this should also apply for that. Huh? Wait, how? How do we know it will work? So for straight line motion, does this actually work? But okay, I mean like your omega is gonna change throughout, and then r squared is equal to r naught v upon omega. Oh come on, this is so not Good. Yeah, velocity is kind of constant. Okay. Perfect. This guy's inertia changes and whatnot. Oh yeah. Okay, this is just the inertia thing. Oh yeah, that's what this is saying. It's saying mr squared times omega. That's our angular momentum. Right. Why not? Think of it like that. MVR. So yeah, this was the initial angular momentum. That's the final. So this will happen for. Why did I think of it? Come on. This equation was this angular momentum conservation. Okay, so at least now we know what how R changes. What else do we know? We know this equation. So I mean how R depends on omega. That is, or more like how omega depends on R. So just omega R squared. That's what we R not. Oh, we want omega squared R, not that. Oof. Let's write this completely using R. Yes. So omega squared will just be R naught squared B squared that upon R naught. Putting that here, we'll just have R double dot, which is the second time derivative of R, minus, right? I mean, this is just getting so complicated, this whole equation, but we have to do it, right? We just have to. Damn, if there was no this, like, if there was no omega squared term, this would be so much better. But there is going to be that term. So we have to solve it the proper way. Okay, R double dot minus R naught squared B squared that upon R power 3 is going to be equal to what kind of equation? I mean, why did they think of putting this? I don't know. Plus, it's supposed to be K, sorry. K L naught upon M. Okay, fine. And now what? It's a function of. Ooh. It's not working. It's not working. Uh-oh. Oh no. Oh no. This is bad. The problem with this is not like simple harmonic motion. It's so much more complicated. Okay. Maximum. Wait, we could just do, okay, why not think about it like this? You want to find the R value for which the R dot would be 0. Right. Think about it like that. So that would just turn this into a, I don't know, biquadratic. Are you serious? No, I don't want to solve this kind of thing. A bi, what? A biquadratic. Even if you take R double dot to be 0 or something, oof, it's gonna be so complicated. There's no way to solve this. Not for general values. You will have to put in values to actually get an equation. And honestly, no, that's just not good. Mass is the mass given? Okay, mass is given, K value is given, L naught is given, R naught is given. Everything is given. Cool. V is also given. Problem is this thing. Yeah. How do I do it? Well, okay. This is really wrong. Oof, this is going to be really wrong. The thing is, R dot might be 0. R double dot is not necessarily 0. Right? Hmm. Hey, we could write this as, okay, R dot dr dot upon dr, right? So like, yeah. So right now I'll use u for the radial velocity. This will be like u du upon dr. Hey, now it's just integration with respect to r of the whole polynomial thing. Except of course this thing, but you get the idea, right? Huh. Might not be that bad actually. So u squared upon 2 and it goes from what to what? Well, initially it's just going to be v. No, initially it's going to be v cosine of whatever. Yeah, u naught squared. Just call it u naught squared. U naught squared upon 2 is equal to, so integration of all that stuff. R power negative 3 integral of that is going to be r naught squared b squared upon negative 2. So it's like negative r naught squared b squared upon 2, and then you got r power negative 2. And it goes from something to something else. Oh god. Right. It doesn't start off at r naught. No. It starts off at l naught. Okay. Oh no. 1 upon r squared minus 1 upon l naught squared. This is not solvable right away. Okay, in general form, this will just take too much of time to even solve. And of course, what we are looking for is when will, I mean, your u be maximum. So, sorry, when will your r be maximum? That is, your r dot should be 0. So for that to happen, you just plug this to be 0, right? Yes. Okay, let's try to solve this properly now. Okay, here we go. It's gonna be minus u naught squared upon 2. So u naught was the r dot thing at just before the whole 4 starts being put on this guy. So yeah, but I don't get it. How else would these people solve a speed in the beginning for which the distance from O to P will reach the maximum value of 1.2 meter? How would you do it? I'm gonna do it like that because I think that's the way to do it, right? Minus u naught squared upon 2 is equal to um, negative r naught squared p squared upon 2, and then you're gonna put 1 upon r squared minus 1 upon l naught squared minus, means integration, right? So minus k upon m r squared, right? So k upon m times 2 as well, sorry. Okay, relax. Yeah, that's how it's gonna be. And then it's gonna be r squared minus l naught squared. Hey, you got some similarities over here, at least. Okay, plus kl naught upon m, and that times r minus r naught. Sorry, l naught. Oh, come on. Right, this would be the thing. And now we would want to solve it. Are you serious? Right, so we'll have to figure out what u naught is and everything. And should I do this? I don't know. Should I do this? Even if I did somehow manage to form an equation, this would be like, I don't know, pi quadratic. Okay, yeah, I mean, you could get that r minus l naught factor. Oh, okay, there's a constant right here. That's not good. So just not doable, right? That's all we can see. It's not doable, right? That's the thing. So it can be done, but not in a sensible manner. Fine, I think we should stop now. So I'll see you in the next video.